Okay, so starting with the warm-up. If P means you are not an only child and Q means you have a sibling, what would the contrapositive be? Carson.
If you do not have a sibling, then you are an only child.
Very good. If you do not or don't have a sibling, then you are an only child. Did we get this right? Okay, is this statement true or false? It's true. Okay, because if you don't have a sibling, then you are an only child. Only people who have siblings or who don't have siblings are only children. Okay. Okay, today what we are learning about is inductive and deductive reasoning. The first one that we're going to talk about is inductive, okay? This is not based on fact, okay? Inductive means that you are looking for patterns. You are making what's called an assumption. Please, under where it says inductive reasoning, please write the word assumption. You are making an assumption. It's not based on fact. You're looking for patterns. Is it already written for you? Okay, I like this lesson a lot because it's kind of like a puzzle, okay? You're going to be given like 3 pieces of a puzzle and you're going to be asked like, what's the 4th piece? And you have to figure out by using inductive reasoning, how could you figure out what the last piece of the puzzle is, okay? So, take a look at the next slide. It's our first example. Describe how to sketch the 4th figure in the pattern, then sketch the 4th figure. First thing, guys, underline the word pattern. Anytime you hear that word, you should automatically think of inductive reasoning. Is this going to be based on facts or based on a pattern? A pattern, okay? That indicates that it's inductive. So, take a look at the figures. What's going on in these 3 figures? What's happening? Hayden?
They're adding by 2 each figure and they're only shooting in one part.
What do you mean they're adding by 2? You're correct, but what are they adding? Good, they're adding more parts, okay? So how many parts does the first figure have? 2. How many parts does the second figure have?
4.
And the third?
6.
So what should be the amount of parts the 4th figure has? 8. So draw a figure that has 8 parts. Draw a circle. And draw 4 lines through it. That'll create 8 parts. Now, it doesn't match exactly. What else do I need to do to my figure? Shade what? One piece, right? But it has to be one specific piece. Hold up is right. Which one do I shade?
You're going to shade, so the left.
The left one where?
Right there.
Just above. Do you guys see that? Should be just above the center line, okay? So you need to shade this one. Why do I need to shade that one? Because that was the pattern. Very good, Benji, okay? We have to follow the pattern. We Gucci with this pattern? Okay, do you see how this could be kind of complicated if we don't do enough practice? Make sure you're doing practice, people. Okay, next one. Describe the pattern in the numbers 5.01, 5.03, 5.05, 5.07. Write the next 3 numbers in the pattern. Does anyone notice the pattern? Sophia? They're all odd. Very good. But more specifically, what's the pattern? John?
It adds by 0.2.
Good. They're adding by 0.02. Plus 0.02. Plus 0.02. So to figure out the next 3 numbers, what do we need to do? Add 0.02. What would be the next number in my sequence? 5.09. Good. What's next? 5.11 and 5.13. Are we Gucci with this pattern? Carson. Numbers such as 3, 4, and 5 are called consecutive integers. What's a consecutive integer? John?
A number that keeps on going up and up, and it's like an integer.
Yeah, it just means that like they're right next to each other on the number line, right? So like if we were to add 1 to 3, we would get 4. If we were to add 1 to 4, we would get 5, okay? Make and test a conjecture. Guys, this is an assumption that we're going to make. We're going to make an assumption about the sum of 3 consecutive numbers. So, what does it mean when it says sum, guys? Add them. So let's start with 3, 4, and 5. Let's take 3 plus 4 plus 5. What do we get when we add those 3 numbers together? You should get 12. Okay. So now, all right. Someone give me another example of 3 consecutive integers. John. 6 plus 7 plus 8. Do the math, people. What are those 3 consecutive numbers going to add up to? 21 is correct, okay? 21 is correct. German, give me 3 other ones. 9 plus 10 plus 11. Add them up. What do you get? Oh my gosh, guys, it's 30. We're just testing them out. We're trying to see if there's a pattern, okay? Add 3 more. What are 3 more? Alex. 12 plus 13 plus 14. I think that gives me 39. Let's do one more for safekeeping. Yeah, Cody. Yeah. Well, in order for them to be consecutive, they have to go by 1, right? Because consecutive integers means they happen one after the other after the other. Okay? Could you give me another example of 3 numbers? 15. Oh, no. Let's make the last one spicy. Like, make them large numbers.
100.
100 plus
146.
what? Those aren't even consecutive. 101 plus 102. Add those 3 together. What do we get? Yeah.
Wait, I have a question. Do they have to be in order?
Yes. That's what consecutive means.
100, 101, and then 100, then 99?
No, because those aren't consecutive. Oh, wait. Yes, you could, but 99 would have to come first. It had to be 99, 100, and 101. What do we get when we add these 3 together, John?
303.
303. Guys, take a look at these. Is there a pattern? What's the pattern, Hayden? No. Yep. What do you get? 4 times 3 gives me? 7 times 3 gives me? 21. 10 times 3 gives me? So if we were to write a conjecture, we would say, write this down. The middle number times 3 was the same as the sum. Good work. Bryson?
Can you go to the bathroom real quick?
Yes. Really, one of my favorite things of all time. This is what we call Pascal's triangle, okay? Now, hold me to this. I'm going to show you a different pattern in Pascal's triangle every day this week.
Lovely.
It's the best thing ever. It's like the coolest. I will show you one today and then one for the following days of the week. What I want you guys to do right now is look at this triangle, okay? You may or may not have seen this triangle before, but try to figure out if there's a pattern. If you notice a pattern, I want you guys in your groups of 3 to write down 3 patterns that you see. Go.
You have to write that.
All right, did anyone get a pattern that they are fairly proud of, that they noticed?
There's a lot of 1.
There's a lot of 1s. Okay, hey, that is actually a pattern. So guys, we could have circled all of these 1s and said this diagonal. This diagonal is all what? All 1s. That's a pattern, guys. That's a pattern. Yeah, Marcus.
Each row, it goes like just one more number.
What do you mean? Ah, very good. So this row had 1 number, this row has 2, this row has 3 numbers, this row has 4 numbers. So they increase the number of numbers in each row by 1. Very good. What else? Benji. Each row has a 1. Excellent. Each row has a 1. Actually, each row has 2 ones except for which row? The first one. It only has 1. Very good. What else? John?
There's 2 threes.
Yes. I wouldn't say that's a pattern. But did anyone circle? I saw some people circle this row. Why did you circle this or this diagonal? Yeah.
You're adding by 1.
Very good. It's all going up by 1, so we're adding 1 each time. Does anyone know how they created this triangle? Okay. So watch. Every single number in this triangle is created by adding the number above to the left with the number above to the right. So start with 1, right? 1, add 1 with, and if there's no number there, add 0. What's 1 plus 0? 1. So you see how it equals 1? Grab this 2. The 2 numbers above are 1 and 1 plus 1 gives you? Do you see this 3? 2 and 1 give you? Do you see this 4? 3 and 1 give you? This 6 came from what 2 numbers? The 3 and the 3. Do you see that? This 4 came from what 2 numbers?
3 and 1.
3 and 1. What about this 10? Where'd this 10 come from? 6 and 4. 15?
10 and 5.
Do you guys see that? Okay.
Oh my.
Now, let me show you one of the really cool applications of this triangle, okay? This triangle is all the 11s to their powers. So start with the first row. 11 to the 0 power is what? 1. Do you guys agree that there's a 1 here? What's 11 to the first power?
1.
11. What's 11 squared?
121.
121. You guys can check me. Take out a calculator. What's 11 to the third power?
1,331.
1,331. 11 to the fourth power? 14,641. Okay, we can keep going, okay? Now, when you get to the tens place, the 1 gets carried. So this would become an 11. This would become a 6 because the 1, like, if you're over, like, 9, right? The tens has to be carried over to the next. Like, when we're adding numbers together in a column, you know how you carry the 1? Carry the 1 when you're doing this. So this last one would be 1,000 or 161,051. And check it. That's going to be 11 to the 5th power. Okay? This is one application of Pascal's triangle. It has thousands of patterns in it. I'm going to show you one each day of the week. Okay? See if you can come up with one on your own. All right, moving on. Something called a counterexample. Okay? So we're done for now talking about patterns. That was inductive reasoning. Something called a counterexample. It's anything that doesn't work for whatever statement you're trying to prove, okay? So if I were to make this statement, you live in Florida, then you live in Miami. If you live in Florida, then you live in Miami. This obviously isn't true. Do you guys agree? Now, that saying it's not true is not a counterexample. You have to come up with something that you can say that proves that this is not true. What would prove that this is not true? John?
Because you can live in like Tampa.
Good. Write the words, you live in Tampa. If you live in Tampa, do you live in Florida?
Yes.
But do you live in Miami?
No.
So this is considered a counterexample. Because it proves whatever statement was there before it wrong. What's another counterexample for this one? Mario? You could live in Naples. Very good. Could you live in Weston? Plantation? Hialeah? Okay? Wherever you live, that's not Miami, that's still in Florida, is a counterexample. Okay? So it's a statement that proves this one wrong. We got it? Okay. Let's find a counterexample for the following scenario. So a student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove the student's conjecture. Their conjecture is the sum of two numbers is always more than the greater number. Are there two numbers you can think of that would disprove this statement? Ronnie? -3 plus 1. What do we get there? -2. What was the greater number in these two numbers?
1.
It was 1, right? Is negative 2 bigger than 1?
No.
So this is a good counterexample. What else would be a good counterexample? I want one more. And don't use a negative number. Don't use a negative number. Cody?
5 plus 4 equals 9.
Well, 9 is bigger than both of them, so that one wouldn't work.
Oh, so it has to be only 1?
So the sum can't be greater than either of the numbers. Cody? 9 plus 0. 9 plus 0 gives me 9. Is 9 bigger than both the other numbers?
Yeah, I mean, not really.
It's equal to 9, so it's not bigger than 9. So this is also a counterexample. Do we see how this is working? So when it says counterexample, you're looking for two numbers or whatever it's asking for that disprove the statement, that tell the statement is incorrect. Got it? Okay. Now we get to deductive reasoning. Yeah. Yes, quickly, 5 minutes. Use facts, definitions, accepted properties, and laws of logic to form a logical argument. Guys, are we looking for patterns anymore? No, these are facts, okay? These are stuff that are definitions. We can prove them. We can show that they exist. Deductive reasoning. This is honestly the more important of the two. Inductive, you're just looking for patterns. What do you assume the next number or the next figure would look like? These have to be facts. You can prove them, okay? The first law in deductive reasoning is the law of detachment. Guys, when you hear the word detachment, what do you think of? Yeah, breaking off or separating. Write the word separate. No. This is law of detachment. Next slide, Cody. Yeah. So, do you guys remember the if-then statements? So, if you're given a conditional statement, that is, if it's Friday, then I eat pizza. The law of detachment says, if the hypothesis is true, so if today is Friday, what can you conclude? You will eat pizza, okay? Circle this. This is your conclusion. So if you're given a conditional statement that says, if this, then this, and it tells you the hypothesis is for sure true, the law of detachment says, separate them, you can conclude the conclusion. You can say the conclusion on its own and be 100% accurate. Okay? So, you see how we wrote the word separate? I want you to draw like a slash between the hypothesis and the conclusion. This is how I think about law of detachment. Separate them. Do you see how the second statement was just the hypothesis? No conclusion. Law of detachment, you can state the conclusion. Does it work in the reverse? So if it said, if it's Friday, then I eat pizza. And then it said, today I ate pizza. Does it have to be Friday? No. Okay? It does not work in the reverse. You can only state the hypothesis and then conclude the conclusion. Questions? Okay. Yes, you need to know how to spell it, okay? The law of syllogism. Detachment, you completely separated them. Do you guys agree? Syllogism, there's a flow, okay? There's a flow. It's like a river. So in syllogism, you're going to have an initial hypothesis that's labeled P. That hypothesis will lead you to a conclusion, which is labeled Q. The next statement will also be a conditional statement, but your hypothesis will be Q, and it'll lead you to another conclusion, which is R. What the law of syllogism says is if both of these conditional statements are true, then you can go straight from the original hypothesis, P, all the way to the last conclusion, which is R. Let's see an example. Next one is the law of syllogism. So, if it's Friday, then I go to the movies. If I go to the movies, then I eat popcorn. Conclusion, if it's Friday, then I eat popcorn. What did they leave out? The movies. So whatever's repeated, you can take out, and that becomes your final statement. Law of syllogism. Bless you. Let's see some examples. If the measure of angle R is in between 90 and 180 degrees, then angle R is obtuse. The measure of angle R is 155 degrees. Using the law of detachment, what statement can you make about the angle? Are we lost? Okay. If the angle R lies between 90 and 180 degrees, do you guys agree this is my hypothesis? Underline it in red. If my hypothesis is that the angle is between 90 and 180, then what's my conclusion? R is obtuse. Do you guys agree with that statement? I do. I agree. If an angle is between 90 and 180, it's obtuse. And then it says the measure of angle R is 155 degrees. Is that stating the hypothesis is correct or the conclusion is correct? The hypothesis. Because it said, what did the hypothesis say? It needs to be between 90 and 180, right? Yeah. Is 155 between those two numbers? Yeah. So we've just stated our hypothesis as true. What can we state as true based on the law of detachment? So detach them, separate them. If this one we know is true, what can we say is true? John?
If 90 degrees is less than m and angle r is less than 180, then I don't know. The 155 is like in between both of them, I guess?
Yeah, 155 is between 90 and 180. Do you guys agree with that? So we just said, okay, our hypothesis is true. Go back to the law of detachment slide. What could we conclude if we were given that our hypothesis is true? Yeah?
155 is obtuse.
Try again. Cody?
Angle R is obtuse.
Angle R is obtuse. Because that was our hypothesis or our conclusion? That was our conclusion. Do you guys agree? So based on the law of detachment, guys, if you're told your hypothesis is correct, if you're told it's true, you can automatically conclude your conclusion. Do you want to see another one? Okay. Last one, it said that the angle was 155. Then we can conclude that the angle must be obtuse. I feel like this isn't clicking.
No.
Okay, let's try. If Janelle gets a job, then she can afford a car. If Janelle can afford a car, then she will drive to school. Oh, this is so for the law syllogism, and then I'll try to create a different example. If Janelle gets a job, then she can afford a car. If Janelle can afford a car, then she will drive to school. Using the law of syllogism, what statement can you make? Identify your P, your Q, and your R. Our P, our initial hypothesis, is Janelle gets a job. Do you guys agree? This is P. What's our conclusion? She can afford a car. Do you guys see how the conclusion is used again as the next hypothesis?
Yeah.
So she can afford a car is the next hypothesis. What's the last conclusion R? She will drive to school. So the law of syllogism says, take out the part that's repeated as a conclusion and hypothesis and just write the first hypothesis. So if Janelle gets a job, then what happens? What can we conclude? Then she will drive to school. Okay, that goes directly from P, bypasses Q, and goes straight to R. Do you guys see that? Kind of? More so than the law of detachment? Okay. I will do another law of detachment problem. Don't worry. What time is this class over?
3 minutes.
3 minutes. Okay, here we go. Which one was Janelle? We did this example? Okay, so between this example of syllogism, let's go back. Hold on. Example 7. State the law of logic that is illustrated. If you get an A on your math test, then you can go to the movies. If you go to the movies, then you can watch your favorite actor. If you get an A on the math test, then you can watch your favorite actor. What law was being used? Law of syllogism. Why isn't it detachment?
Because you're not attaching to your conclusion.
Good. Okay? If they're ever all conditional statements, if they're all if then, it's always going to be syllogism. Okay? Detachment states stuff as a fact. It's like if this, then this. Then it tells you this happened, what can you conclude? Not if then, okay? Did? Oh, here. If x, go to example 8. If x is greater than 12, then x plus 9 is greater than 20. Underline your hypothesis and your conclusion. This is our hypothesis. This is your conclusion. Do you guys agree? It says the value of 14, the value of x is 14. Do you see how that's a statement? It's not another if then. Therefore, x plus 9 is greater than 20. It stated our hypothesis on its own, and then it stated our conclusion as a conclusion on its own. What law was being applied here? This is the law of detachment. You have to view them as separate statements. So it's no longer a conditional. It's no longer an if-then. If it breaks it up and just says the value of x is 14, therefore x plus 9 is greater than 20. Just like we did in the last one. Okay. And the... I'm going to make up my own problem. Write this down. Add a slide before example 9. Before we go, so you guys understand law of detachment. Law of detachment. Okay, let's say if you have money, then you can go to, I don't know, the movies. And then what if I said, you have money? What can I conclude from the law of detachment as my last statement? What am I able to infer based on this? Cody? You can go to the movies. Do you guys see how the law of detachment states stuff as a fact? It's like boom, and then the last one is boom. The law of syllogism kind of flowed. It had two if-thens, and then you can label the last if-then. Okay? Law of detachment is break them apart. State your hypothesis, and then state your conclusion. This is where... So we have x squared is greater than 25 being used as a hypothesis and a conclusion. But remember, for law of syllogism, it needs to be used as the conclusion first and then the hypothesis. So what do I need to do to these two statements? Just reverse them, right? Write the second one first. So we're just going to write it in the exact same way, just in reverse. So if x is greater than 5, then x squared is greater than 25. And then it says if x squared is greater than 25, then x squared is greater than 20. Highlight the repeated portion again. That's our cue. And let's draw out the letters so we can see what's happening. So this x is greater than 5 is our P. Then we go to Q. Then we have Q again. And what's x squared is greater than 20? What should I label that? Anyone remember from yesterday? R. Very good. That's our R. So in the law of syllogism, it says if you have two conditionals and your conclusion from the first one is the hypothesis of the second, you can jump straight from P and go to what? R. So what's our final conclusion based on the law of syllogism? Carson?
If x is greater than 5, then x squared is greater than 20.
Excellent. Very good. If x is greater than 5, then x squared is greater than 20. What was taken out from the conditionals? What was taken out? Carson? Q. Very good. The x squared is greater than 25. Questions, guys? Do we all see that? John?
So like P is in like to R
Mm-hmm.
at the end of the day?
Yep. So P to Q, Q to R, then you go straight from P to R. Very good. Yeah.
Do you have all the salads?
Have them this? No, I have them tomorrow morning. Mm-hmm. Try the second one. So law of syllogism, look for the repeated section. What's the repeated statement, guys? German? A polygon is regular. Highlight it, guys. A polygon is regular. What's different about this one, though? Ronnie?
It's like at the hypothesis.
It's in the hypothesis for both. Do you guys agree? Can we use the law of syllogism with something like this? No. Okay? This is an example where the law of syllogism is not possible. Okay? It must be used once as a hypothesis and once as what? A conclusion. Did either of these get used as a conclusion?
No.
No, so we can't use it for law of syllogism. Okay? If they're both used as a conclusion, so if these were both used as conclusions, could we use the law of syllogism? No. They have to be used one for hypothesis, one for conclusion. Correct. And remember, you may have to reorganize it so it's conclusion then hypothesis like we did in the first one. Do you guys see that? Did we do the Janelle example yesterday? Two examples on this page. Those are the only ways I can throw the law of syllogism at you. Either it can't be used because it's used twice as the hypothesis or twice as the conclusion, or you have to reverse the order, or it's set up perfectly for you. Okay? Any questions on law of syllogism? Last ones, okay? This is not syllogism or detachment, okay? This is inductive versus deductive. Before we read these questions, we're gonna decide whether we're using deductive or inductive reasoning. Do you guys remember what inductive meant? John? Or no, Ronnie? It's a pattern, very good. Write that above it. You're looking for a pattern. What was deductive? Flow is syllogism. Remember, syllogism is a form of deductive reasoning. Who remembers what deductive meant? John?
Not a pattern?
Kind of.
Oh, it's not like
No, it's not a guess.
like facts.
Good. It's facts or definitions. These ones, everything has to be 100% true. You're not analyzing a pattern at all. Okay. So let's read the first statement together. Each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball up in the air, it will return to the ground. Is Monica making an observation based on a pattern, or is she using facts?
Facts.
Is there an example where you could kick a ball up in the air and it would not hit the ground?
No.
What would happen? What could happen? Yep.
It gets stuck on the roof.
It could get stuck on the roof. What if it gets caught in a tree? So is it a fact that the ball will hit the ground? No. And notice, guys, please underline these two statements. If it ever says each time and next time, do you agree she's looking for a pattern? She's saying each time she kicks the ball, it comes back down. Do you guys agree?
Yeah.
So is it likely that the ball will come back down? Is it 100% guaranteed? No, she's looking at a pattern. Do you guys agree? So this is inductive reasoning.
Mr. Jurko?
Yeah.
On the quiz, is it gonna be like, have directions like that?
Mm-hmm. Mm-hmm.
Yeah.
B, all reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile.
So
Is this pattern or facts? These are facts. Is there any pattern that's going on here? No, everything that was stated was a fact. So what kind of reasoning is this? This is deductive. Okay. What do we still have questions on? Everything? Cody, give me an example. What do you want me to review with you? This is an example of syllogism. Let's say we started with if your brother is athletic, then he plays sports. If your brother plays sports, then he's in shape. Using the law of syllogism, what is the final conditional statement that we can write? Using the law of syllogism, what is the final conditional statement that we can write? John?
Wait, what do you mean? Wait, I'm confused. Never mind.
Alexis?
Your brother plays sports.
No, that would be detachment. Carson?
If your brother is athletic, then he's in shape.
Very good. If your brother is athletic, then he's in shape. Does anyone know where that came from? How did we get there? Cody?
So it goes, your hypothesis is if your brother is athletic.
Okay.
And then your conclusion, then he plays sports.
Okay.
And then for the second sentence would be, if your brother plays sports, that would be the Q.
Mm-hmm.
And then the R would be he is.
Excellent. So when we're using the law of syllogism, we go straight from what to what? P to R, okay? You take out what? The Q. So you can jump straight from the original hypothesis down to the last conclusion. So if your brother is athletic, then he's in shape. Alexis, does that help doing that example? A little bit? Okay, you're gonna get a lot of practice in the homework. So how many people have started the homework, be honest? Okay, that's decent.